This is quantum mechanics in 3D. This is basically take it up from where we last left off, and these lectures are micro lectures in the fact that people often don't have time to go through long-winded lectures when the principles can be explained in such a short amount of time. So that was my aim all along for this channel. But anyway, our Hamiltonian in Cartesian coordinates is the sum of the kinetic and potential energy, and is given here. And after doing the appropriate transforms to make it more quantum mechanical, with as you'll recognise here, that h bar is the Planck's constant. Well, it's the Planck's constant over 2 pi h bar, and the three coordinates partial derivatives over x, y, and z. Second partial derivatives over x, y, z, plus the potential term at the end of x, y, z, and the time-independent Schrödinger equation in this form would be given here. If you write this out in full, for the Coulomb potential between two charges, it gives this here. And now the problem. Now this becomes a big problem, because although this simplifies the kinetic energy terms like x, y, z, which is abundantly clear to see, it's the potential energy terms now between the two charges. We have they are given over the square root of x squared plus y squared plus z squared, and we're not going to be able to write it in a form of separate variables here of x, y, z. So they're just not appropriate basically for what we, and they're not appropriate at all really for any real world situations, because atoms aren't cubes or squares. But we can if we solve three separate equations, no, we can't write this and solve three separate equations because of the potential energy term. So we need to transform to a spherical coordinates, which is obviously more appropriate. So we transform the Laplacian here. Well, we first put this into the time-independent Schrödinger equation here, and using the Laplacian in spherical coordinates is given here. This can be looked up on, just put it into Google, Mojik, whatever your search engine is. It takes 2 seconds, it will come up with this. Just put in the Laplacian in spherical coordinates and this will come up. And I think I once did a video deriving this. If I haven't, I probably will do at some point. Sorry. But that's not important in the time being. So we take the last two terms of the Laplacian here, and we obtain this, the x hat, which is the angular parts, and so the full Laplacian becomes this plus the x hat, which this here is the radial part. So the time-independent Schrödinger equation will then come simplified down to this form. Now the potential as a simplified term, but the kinetic term is much more complicated now. But this is separable, unlike the first time. But now it turns out that x hat is the operator L hat squared, which I think we have come across this before in probably the previous quantum mechanics video with angular momentum. But anyway, this represents the I can't see what I've wrote there. This represents the of orbital angular momentum, the total orbital spin total angular momentum. But here LZ equals IH bar, the partial derivative with respect to phi, and that's LZ. So we have L of X, L of Y given here, which are obviously the most complicated terms containing cotangents and things like that we really don't want to mess around with. I think these can be solved, but it's just not worth it, because we can, for all intents and purposes, just use Z. But now from from the equations given before, we have x hat, so this would become x hat equals minus L hat squared over h bar squared over r squared, after taking in the above equations as well and solving for x hat. So the time independent Schrodinger equation here, it becomes this in the form of total angular momentum L hat squared. Now this equation is separable and is in the form of this, where this is the radial component and this is the spherical harmonics. So we now get two equations, R of R, y, theta and phi, and we can label by the separation constant k. So we will get it in this form then, the equation. Here L squared acting upon the this is the total angular momentum operator acting upon the spherical harmonics, which would give this k, and then multiply by the spherical harmonics, which is the eigenvalue of the operator L squared, the total angular momentum operator. This means that the spherical harmonics is an eigenfunction of the total angular momentum squared operator, and k is an eigenvalue. The allowed values of k are L plus 1, h bar, where L equals 0, 1, 2, ... which is the orbital angular momentum quantum number. Hence we obtain this equation. Now now we have the radial part here, and this is the Hamiltonian and the total angular momentum operator and LZ angular momentum operator. But the eigenvalue for the equation LZ can be written as given here. So we want solutions of the form given here, and the solutions here is a very basic partial differential equation, is the simplest one in these spherical coordinate systems, and it's given here, where minus m squared is the separation constant, and so LZ hat operating on E I m phi, which will be the solution of this basic differential equation, and we would end up with this, where m is the magnetic or azimuthal quantum number. I think I've been through this before. And in terms of h bar, well, 0 plus minus h plus minus 2h, and so on and so on. Now we will have this form when it comes to this is the spherical harmonics, because it's in terms of phi and theta. In fact there's only the phi terms left here, the constants, but they're like yeah, we substitute this as a constant. We will get m squared over sine squared theta, which equals L plus 1. And we set L equals m equals 0. And now we have found L equals 0 and m equals 0, the spherical harmonic, which gives this as sine theta. And now minus 1 over sine theta, cosine squared theta minus sine squared theta, plus m squared over sine squared equals LLH bar sine theta, which again simplifies to this. Then we're using the identity, which cosine squared plus sine squared equals 1, and we will get the equation here. And this holds for all values of theta, if and only if L equals 1 and m squared equals 1. Aside from normalization, we have found solutions for L equals 1, m equals minus 1, and L equals 1, m equals 1. And these relate to the first excited state of hydrogen. And just for show, these are the first few spherical harmonics here, where L and m, and 0, 1, 1, 1, 0, 0, minus 1, 1. Well, you can see basically, and I've just dotted it going down here because there's obviously a lot more. But yeah, that will be it for this lecture. Please do subscribe. There's a lot more to come.